most strategic planning engineers have likely faced the question of whether it is necessary to relocate structures and utilities to expand a mining pit. In this video, we will try to demonstrate an example of how this issue can be resolved. We will also explore how to apply constraints to the algorithm for determining optimal pit boundaries. To begin with, we need to have the structures placed on the plan, along with safety zones where the pit should not be located. We have a simple optimization project prepared with all necessary parameters set. Currently, it has no constraints. By the way, this scenario should be executed first, the no constraints case. It allows us to see where the pit tends to expand without any restrictions. Let's observe how the pit expansion progresses, in which direction it moves, as the price adjustment factor increases. We see that it gradually expands in the central part and then reaches the western section, which will require additional constraints. Since these constraint boundaries are reached fairly quickly, it is worth considering evaluating the cost of relocating the object and incorporating it into the optimization project, taking its price into account. However, this is just an example and a demonstration of how the analysis can be structured. We can see that the potential pit extends beneath all the structures located on the plan. This allows us to visually assess the impact of applying constraints in the calculation. Now, let's add exclusion zones. For example, the power station cannot be relocated. We add this object to the exclusion zones menu. In the Capex menu, we create 3 different fields and fill them according to the cost of performing work for each of them. For example, we can use the provided Capex values. Now let's see how our pit will expand with these input data. As we can see, the exclusion zone has worked, and the pit development does not affect the area where the substation is located. Next, let's observe how the pit develops near the industrial site. Up to a price adjustment coefficient of 0.8, the site remains untouched. However, from 0.8 onward, the blocks of the site start to be included in the extraction process. This can also be observed in the table, which shows at what point the capital expenditures begin to increase. Now, let's consider a scenario with higher capital expenditures. The pit development continues toward the restricted site, halts, accumulates profit, and then resumes extraction, but only starting from a coefficient of 0.95. This indicates that the price of the final product must be at least 0.95 of the specified value. Only in this case does extracting the industrial site become economically feasible. In the previous case, the threshold price adjustment coefficient for extracting the entire site was 0.85, whereas now it is increased to 0.95. As for the exclusion zone, everything remains stable as expected. Now, let's compare the calculation results. In the scenario with the highest Capex, the amount of ore extracted is the lowest across different coefficients. The increase only occurs at the key coefficient mentioned earlier. In the scenario with lower Capex, the coefficient at which ore extraction begins is slightly lower, but eventually, the same level is reached over time. If we consider the no constraints scenario, we can see that the amount of extracted ore is significantly higher. This is due to the exclusion zone not being included in the pit's working area. A small surface section can block 5 million tons of valuable ore, and that's not even the limit. Finally, let's take a look at the results on the graph. The difference in the increase in mined mass across different coefficients is evident. The higher the capital expenditures, the steeper the growth at one of the key coefficients. So, experiment, analyze, and don't forget about these crucial features of the optimal pit boundaries module. And enjoy the results.